Alright, so now we're going to talk about multiplication rule in terms of complements and conditional probabilities. This is again following Triola's book where we're talking about section 4.5. So in previous section we had talked about the probability of getting exactly 3 heads, and we had talked about the sample space here, and we talked about there's 8 possible outcomes and 3 of those gave exactly 2 heads. But some of you had wanted to go, well, you said 2 in 3. Well, why doesn't that include 3? Well, I had said I didn't say at least, I just said 2 heads, and I meant exactly if I don't specify. So in this one, we're going to specify. We're going to say at least 1 head. So this time around, we're going to talk about at least 1 head. So that would be 1 head or more, right? So being greater than or equal to 1 head, that means 1 or 2 or 3. So we're going to include the 1 head examples, the 2 head examples, and the 3 head examples. And so that's what we're going to look at here. So if we go and say what's the probability that the number of heads is at least 1, right, greater than or equal to 1, then we're talking about the probability that we have a number of heads equal to 1 plus the probability of the number of heads equal to 2 plus the probability that the number of heads is equal to 3. Now what you're seeing here is the addition rule, right? Compound events happening, 1 head or 2 heads or 3 heads. And we could look at it very much like that sum. So the 1 head example, right? There's 1, 2, and 3 possibilities where we have 1 head. So that would be, 3 out of 8. And then plus, and then the 2 heads, we talked about that one before. There are 3 out of 8 there. And then we talk about the last one where there's all heads, and that's only 1 out of 8 there. And so we could find it that way. So that would be 6 plus 1, which is 7 eighths. However, the probability of greater than or equal to its complement, right, the complement of that greater than or equal to, it is less than 1 head. So complement of greater than or equal to 1 is less than 1. And then what we want to talk about is the fact that being less than 1, this probability right here, that probability of being less than 1, so the head is less than 1, well, that's really the probability of them being all tails. That's another way of looking at that, isn't it? But that in and of itself is 1 minus the probability that we get the random variable x equaling to, or h, sorry, change that back to h as we were talking about. That's the probability that h is equal to, it's actually equal to 0. And so that's another way that we could look at this. No heads, right? And all tails, this is probability that they're all tails, is one of them, or the probability that we have tails is equal to the probability that we have 0 heads. So that is what we can say is at least this is, yeah, that was right. So 1 minus the probability there, and this is the probability that they're less than 1 tail is, yeah, okay, so this is the probability that we have the heads is at least 1 is equal to 1 minus the probability that we have 0 heads. So the probability of having 0 heads, that's the only place that that happens. So we see that this looks like 1 minus 1/8, which is going to be equal to our 7/8 there. So complements of being less than or equal to and greater than, or greater than or equal to and strictly less than, we want to pay attention to that. Okay, so you see this greater than or equal to, its complement is less than. And what I'm telling you in addition is that if you look at the less than or equal to, then its complement is going to be strictly greater than. So these are the things that we're looking at in terms of inequalities that are actually going to become quite important in our binomial distribution in the next chapter. So this is complements, and if we have greater than or equal to, its complement is going to be strictly less than. And we saw that in terms of our two probabilities up there. All right, so if I say less than 5, then the probability is the 1 minus the probability of at least 5. So those are complements as well. So remember some of our translations here. More than, if I say more than, that means I'm talking about a greater than, a strict inequality. If I say at least is a translation for greater than or equal to. If I say at most, that is a translation for less than or equal to. And then the other one that I might use would be fewer or less than, right? And those both translate to the strict less than inequality. And so those are a couple of translations, or a few translations that you may run across that could be important to you. All right, now, what is the probability of getting less than 2 heads when flipping 3 coins? Well, we just solved that problem, didn't we? Less than 2 heads, if we are looking at this, we can say, okay, well, less than 2 heads. How can we translate that? So the probability of less than 2 heads, so H is less than 2. Well, that would be the probability, 1 minus the probability that heads is greater than or equal to 2. And we know from past experience that this is going to be, this is going to be our equal to 2 and then equal to 3. And so we knew from before that that was 1/2 because 4/8, right? And so the probability that there are less than 2 heads is the same as the probability that they're greater than 2 heads. Now let's take a look and see what we see here. Less than 2 heads. So no, 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 yes, that's 1. Less than 2 heads? No. Less than 2 heads? Yes. Less than 2 heads? Yes. So that's our 3, and then there's our 4th one with less than 2 heads being 0 heads, right? So we can see those two probabilities come out in that respect as well. Okay, so let's take a look at this next example, and this is one of Triola's book examples. So I like to cover this for Triola especially because it gives you some of this work that we're talking about. So a blood testing procedure is made more efficient by combining samples of blood specimens. If samples from 5 people are combined and mixed, and the mixtures test negative, then we know all 5 individuals are negative. If we want to find the probability of a positive result for 5 samples combined into one mixture, assuming the testing positive is 0.00 or 0.015. So we want to define the problem in terms of probability notation. So what we have is, let's call these